Perfect. Okay, good afternoon, everybody. Thanks for joining today's ACIT seminar. We are delighted to have Dr. Hieu Nguyen as a speaker today. He's currently an assistant professor in the Department of Electrical and Computer Engineering at North Carolina A&T State University. Before joining NC&T University, he was a postdoc at Center of Energy, Economic, and Environmental Policies at Rutgers University, 2019-2020, and then University of Utah and Department of Electrical and Computer Engineering at Iowa State Universities. So he received his PhD degree from the University of Quebec in 2017. He did his master degree in electrical engineering from Southern Taiwan University in 2012, and Bachelor of Science degree in control automation from Hanoi University of Science and Technology, Vietnam in 2010. Without further ado, I would like to invite Dr. Nguyen to give us today's talk. The stage is yours.
Okay. Thank you very much, Dr. Good evening. I'm very. I hope that there are some. I hope I don't have any issue. Okay. It's my pleasure to present some of my research work today to the seminar. My name is Hieu Nguyen, and I'm just joined ACIT in the January 2021. And today I would like to talk about power system resilience with distributed flexibility from energy customer. And I hope you enjoy my talk. Okay, so the reason so basically power system resilience is a part of my research team, and I would like to continue working on this at North Carolina. So basically, the motivation behind that is that due to climate change, we face a lot of problem with a natural disaster in the context of United States, and you can see that the damage induced by natural disaster are increasing over time, and the reason, the very reason issue we face in 2021 is ice storm in Texas. Okay, so the storm out, so we result in the loss of load of the whole state of Texas. Okay, so in terms of natural disaster, there are different types of disasters. So we have wildfire, we have hurricanes, we have the earthquake. So here it just some capture some picture to illustrate different type of natural disaster that affect the United States. So when I live in Utah, I mean in 2000. So I came with a natural disaster topic. I think when I start my postdoc at Iowa State, and at that time, there are a lot of cyclone. So actually, it's also the nickname of the Iowa State University cyclone. So basically, there are sudden disturbance in the wind and also thunderstorm, and it's sometimes it creates a lot of outage. And I myself experienced some outage during living in Iowa. So I actually working on power system resilience when I moved to Utah. And at that time, there are two topics. Okay, one is hurricane, and one is wildfire. So actually, at the Utah, when I work on a hurricane, the main concern of the people in Utah and also more part of the western of the United States is the wildfire. So they are not really concerned about hurricane. So when I moved to New Jersey and now North Carolina, so I think I realized that the critical issue, the most damage, these natural disaster in the East Coast, tend to be hurricane and winter storm. With that, just some illustration, different type of disaster and how you affect different regions of the United States. So depend on the region that we live, we may want to have some different resilient strategy to cope with this one. And in term of the electric grid, we will have different happening strategy preparation and adaptation accordingly. For example, for the wildfire, the critical part is how to improve the situation awareness, because the issue with the wildfire is that some of them caused by the power system. So how to detect the fault in the power system accordingly to prevent power system ignite the wildfire. In the case of the hurricane, okay, air power engineering, we do not create any hurricane. Okay, so that is the common sense. So the issue is that when a hurricane caused by the nature, it comes and it can blow up our electric pole. So the different approach is hard. So we have to have a different approach. For example, how to build stronger electric pole, how to improve the structure of the overhead distribution system, or basically just make it underground. Okay. And for flooding, unfortunately, it affects the underground cable. So how to make the system resilient to potential flooding. So different disaster, they result in different strategy. However, they come up with result in very common definition. I mean, criteria how to cope with this one. So that's why we have the concept of resilience. So let me talk a little bit about the history of the resilient concept. So basically, it's like I think it's like 700 years ago. We have the word resilience when it's talk about some contract termination and restoration, some legal situation. So it comes from some finance. So then we use the word resilient to explain some type of goods that were able to accommodate a sudden and severe load without breaking. So it came to the civil engineering first. Then we improve it, to apply its concept to some kind of material and constructions. And in 1973, okay, we Crawford Holding, introduced the concept of resilience to ecology and environment. So basically, at that time, we want to expand this concept, as a persistence of system and the ability to absorb change and disturbance. And lastly, we come up with the term, power system. Okay, so we adapt the resilient concept to power system. And the first concept in 1977, okay, written in the article of Harmony Loving, Resilient in Energy Strategy. Of course, right now we expand it. For example, not only engineering system, we also expand it to social system. So so basically, it the ability to withstand external shock. Okay, so for power, so in its case, it's a social infrastructure. So basically, come back to the main theme, the engineering aspect of the National Infrastructure Advisory Council as it defends the resilience of the critical structure. Is the ability to reduce the magnitude or duration of disruptive event. And the effective resilient infrastructure or enterprise depends upon its ability to anticipate, absorb, adapt to, or rapidly recover from potentially disruptive events. So basically, it takes a long time to have a good definition about the resilient. So basically, resilient is the ability to prepare for and adapt to changing conditions and withstand and recovery rapidly from disruption. So basically, resilient focus on high impact and low probability events. On the other hand, we have a very traditional, concept of reliability. So basically, reliability focus on high probability but low impact events. Okay. So here is a comparison between resilience and reliability. So for example, during so a reliable grid is that a grid can support the electricity to customer without disruption during normal weather event. So it's an example. Okay. So during a very for extreme weather events such as hurricane or something, we do not expect that we can serve 100% customer, but we want to make sure that we can serve as much customer as possible. Also, once the hurricane finish, we want to restore the power system as much as possible. So it is the difference between resilience and reliability, and also the metric to quantify the system accordingly. Okay. So why we need resilient, concept for power system, and why power system resilience become a very hot topic these days. So basically, we know that the power system is very vulnerable to natural disaster. So if the wind becomes so strong, it can blow up or damage the overhead power lines. Okay. And in the context of North Carolina, I believe that hurricane and wind storm, winter storm, are the most dangerous factor. Okay, so basically, you can see that in the picture. I just want to show one of the model we often use to quantify the fragility of the system. So basically, in the hurricane, most utility they have the fragility curve. And you see that, basically it represents the thing that, when the wind speed increase, the probability of failure of the component, also increase accordingly. And then on the right hand side, it just shows that, the report about, the damage of the power system caused by the Hurricane Matthew in 2016. Yeah. And also, I think that at that time, North Carolina also a part of this, impacted area. Okay, so basically, how we talk, we have the common sense that natural disaster can damage the power grid. So how we adapt to that? So basically, we have the concept of resilient curve. So that means that when we have the disturbance over here, the system will be degraded accordingly. So some power line will be damaged, some substation will cannot be working. Okay, so so once the disturbance is over, we need to assess the system and recover it accordingly. So we call it the resilient trapezoids. So we want what resilient action is that we want to reduce the area of these trapezoids. So we want to put it the system we want to serve more customer. We want to reduce the time of restoration. So basically, this is the area that we want to reduce, and the value of area to show us how the system is resilient to any kind of physical disturbance. Okay, so the smaller of this trapezoid, the better. So in order to do that, we have to have a very good timeline of action. So for example, in the pre-disturbance resilient state, okay, we have to do some planning, long-term or short-term. So long-term planning means that, we have to identify the system vulnerability and have some, long-term investment accordingly. For example, building new generation plants, or building a new infrastructure to deliver electricity, so we have a more redundant in the grid. So it's a long-term investment. In the short term, we have to prepare for that. For example, we have to before the hurricane, we tend to have pre-positioning some resorts. So if anything happens, we can have a resort to support the customer locally. The resort can be mobile generator, mobile energy storage, or some utility crew. So one that can be dispatched to fix to repair the damaged component subsequently. And once the disturbance is over, for example, the hurricane is over, okay, we need to have ability to assess the system, so we know which component is damaged, and the location, we need to send people to repair the component. Okay, so we need to identify and assess the damage. Then once the damage is set, okay, we need to repair this and restore the service, step by step until it come back to the post to the normal operation. So if we can have a good resilient action plan like this, we can improve the system the resilience of the system significantly by reducing this area. So for my research, actually I haven't worked on repair and restoration yet. Related to I think it's focused on my future work. Currently, so I have some work on the planning to basically identify some critical component such that if it damaged, it can result in a very high cost for the whole system. We have some work. We have a work on the preparation, so how to prepare the system, before the hurricane. Okay. We also have a work on, so assessing some impact of energy resources on, the system on the power system, again the hurricane. Okay, so basically, if we have more energy storage, we can, improve the energy, the number of customers we can serve, during the outage area. So in the for hurricane, so I also have a work, on, just quantify the probability of Wi-Fi ignition caused by power distribution line. So basically, the idea is that if any phone in the power distribution grid, okay, there are some, arc that ignites, and the arc, okay, with a very high temperature can, hit some burnable material such as tree or wood. And that caused the wildfire. So it is the case of the wildfire in California. I think it's 2019 or 2018. I don't remember exactly. And also it 20 years ago in 2000. It is the case of the wildfire ignite in Australia. Called it the Black Tuesdays. So anyway, so I think due from this I will talk a little bit about my work on on the preparatory operation of automated distribution system against the hurricane. So basically, in this work, I just want to focus on the short-term operation of the grid. When the hurricane happened, how to prepare that, and after the outage, he identified how I can restore the load to the customer, accordingly. So the idea is that how to optimize the preparation and the post restoration, in the co-optimization way. And more important, and another point is that how to allocate power to customer based on the CIC rates. So I will explain it later, but the idea is that we want to ensure some equity in the restoration. We don't want to ignore a certain number of customers during the restoration. Okay. Okay. So that is in order to do that, the first step is to model the power grid outage induced by hurricane. So basically, we have the velocity curve I presented in the previous slide. It shows the probability of failure to the and the function of the wind speeds, and based on the probability of failure, I can generate a certain number of lines that in be that is damaged by the wind speed. And the question is that how to get it wind speed is based on some hurricane model. So we call it a spatial temporal hurricane model. And of course, currently there are several research that want to have a better model of the hurricane. But that if you can predict the wind speed, the gust wind speed, accurately, you can have more accurate model of the impact on the power grid, and consequently, you have a better strategy to counter this outage. Basically, so we have a set of a spatial temporal hurricane in view line outage. So we have the name of the line and also the status of the line during 24 hour. Here here is in the y exit is the number of the time slot. We have the 24 hour. We have each time slot is 15 minutes. So we have a 36 hour. The reason is that the peak we have, you see that if you look at it, you see that most of the outage happen at the same time. So basically, it is a time that the hurricane hits the power grid. And by the way, when the line is damaged, we assume that it cannot be repaired immediately. We need to wait for a while until the hurricane is over in order to send equipment and human to repair the distribution line. Oh, so that is so. Anyway, so we have the preparation in the first step, and we have a lot of uncertainty depend on what kind of scenario realize in reality. So we have some uncertainty in the second step. So that's why we call it a two-step stochastic program to model the optimization of the preparation and restoration. So this co-optimization is a stochastic program. The difference between both states is that in the first state, all the decision variable must be scenario independent. So basically, we have very a cost-based objective. Okay, we try to minimize some of the economic cost related to energy import from the upper grid, and also utilize the generator. However, we have a term named E-code over here, which is the main component of the one. So E-code is the expected cost of energy not served. So we have the probability. We multiply with the rate of the customer interaction cost, multiply with the number with the value of the the value of the load curtailment. So basically, and because we multiply, we take the sum of all the possible scenarios. That's why it's an expectation. So it is the expect cost of energy not served. Okay, so that's it. So basically, we try to minimize the expected cost of energy not served of all customer in the power grid. And why we also want to minimize a little bit about the economic cost related to this preparation and restoration. So it is a core optimization problem. This problem, of course, subject to several constraints, because here I have some constraint of distributed energy resources, constraint about the substation, how to import energy from the upstream transmission network. Okay, with there some capacity, some constraint related to the operation of the substation, and also other constraint. But the key idea, one of the more important constraints is that how to capture the power flow in the distribution network accordingly. I'm not going detail about this, but basically we have the normal operation of the power grid with written in the form of a power flow. But right now we have to include some auxiliary variable to model the power flow equation in both pre-outage and post-outage scenario. So basically in pre-outage, so the power equation still there, but in post-outage scenario, if the line damage, we have to make sure that the power flow in this line equal to 0. And we want to do this in a compact way, so that we can write both cases in a single equation. So we can put it inside mixed integral linear mixed integral optimization model to solve that instead, because instead of using any if-then expression. So basically, it is the critical part how to model power flow constraint with the line outage status. So we have here, it's a normal operation constraint. So we have a set of nonlinear equation, and if we relax some equation about it, I have a set of connect programming constraint. Then I put some line status over there. So basically, here here there's an auxiliary variable in related to the voltage. If it equal to if the line is not disconnected, if the line is connected, it equal to 0. So basically, it means that the voltage in both terminals equal to 0 and no power. When I integrate this one in this equation, I have a new power flow model that can model exactly the connected and disconnected line simultaneously. So I put it with some simulation data. I try to show it in the actually 13-bus test figure with three type load. So here I show you three type load: non-critical, moderate, critical, and critical. Okay, both of them have different type of CIC rates. And the thing here is that you can see that the CIC have a function of the load type and also the duration of outage. So if the load is not served for a certain time, okay, its CIC value will increase accordingly. So by doing that, we understand that the priority of restoring this customer will increase over time if you do not serve him or her. So by using this code of CIC, okay, at some point, people with initial low tide, they have they will be allocated more priority in the load restoration. So we will not ignore them. So we test with I think it's 4 cases. So I named from so I index it from 0, 1, 2, 3. Actually, the case 0 is a very dummy case to show that if there are no energy no distributed energy resources, there are no resilient, okay, because there are no adaptation to the system. So we test with server K, and we use this kind of outage scenario for illustration. So basically, if you see this K1, we have the energy storage, but we do not have any distributed energy resources. You realize that we have to you see that we have a certain limitation in terms of load restoration. So here for you see that okay, for even for a critical load, it need to wait some time before restore because we have some limited resources in the system to serve them for the entirely post hurricane time slot. For when we have more resources with DZ, we see that okay, we can serve critical loads the whole time. We have a little bit we also can serve non mediumly critical load at some point, and critical load nearly at the end of time slot. I visualize it in terms of resilient curve over here. So basically, when we have no resources, okay, there are no resilience, so it's we cannot serve them during the post hurricane outage. You see that it's reduced over here. For when we have more resource, okay, we can serve more customer. You see that it go up over here. But the thing, and when we have a unlimited resource, remember that we can input up the supply certain, but we still have some limitation here because there are some part of the load we don't, we do not have any resources to support them because some due to some disconnection, like isolated area. Okay, so basically, but the point I would like to say is that okay, so all the customer here at some point will be restored based on their CIC value. And why we want to mention that? Because in reality, we only in reality because in reality the critical issue right now is that how to fairly allocate a customer and energy to serve customer in the port outage. And actually, it's a reason case in New York. People realize that a certain area is not put enough priority in the load restoration. So how to put some metric into the system to improve the equity of the restoration is a critical issue. In our work, we use a very simple CIC, increasing over time. It shows that it's better than, you given a fixed value. What you know that if we just given a fixed value of the CIC, people just restore the ones that have the latest interruption cost. So they only focus on restore the critical customer. They will ignore, non-critical one. Here with the CIC, when the outage duration increase, at some point we have to pay attention to them. So that is the idea of integrate the CIC into this framework. Of course, in order to put it in other optimization is very challenging because the CIC depend on the outage duration, and the outage duration here, depend on our action to restore the load. So it's not really a parameter anymore. It's some kind of depending on our variable. So it makes the optimization problem become more complicated for other application. Yeah. So that's it. Do you how much time left? So I still have a nice slide.
So I think still you have about 10 minutes.
10 minutes. Okay. Okay. So basically, it is the thing I talk. So next, I just want to talk a little bit about some of the current work that we focus on how to use like more active demand side management of our customer, and potentially it can be help to boost the resilience of the distribution grid. Remember that the previous work I focused on utility based resources like large energy resources and distributed generator. All are controlled by the utility, so the utility can optimize the operation sent in a centralized way. However, right now if we have more smart appliances at the demand side, it implies that if we can manage them efficiently, we can contribute a little bit. We can contribute to the grid resilience. So basically here we see that it's a normal operation of a typical distribution network. We see that without any control, okay, the load is not so smooth. So recently with a lot of smart smart controller at the distribution side, the question is that can we adjust the power consumption of the power of the whole power distribution network accordingly. So basically, here there an example we in our current project. Of course, so basically, if we have the distribution load over here, based on the feedback of distribution load, the question is that how we make the power distribution system energy consumption follow some reference. Okay, so it's an example. And of course, for the sake of publication, of course, we want to put it in a better name or more catchy name. For example, risk-based mechanism design for transactive energy market with massively distributed resources. But the idea behind that is very simple. It's just like a load compensation problem and how to control it on off accordingly. Okay, so in this work, we try to implement this thing on a smart distribution network. And we realize this feedback, using some code simulation. And the idea is that how to design this, control on of signal via pricing, so we can do that in a distributed way to make the distributions power energy consumption follow some targeted load. I will talk about some implications about power system resilience later. So how to do that? So basically, we will ask the customer the smart thermostat, report the condition they want to consume power. For example, here we want them to send me a bit. For example, how much energy they want to pay for a certain amount of how much dollar they want to pay for a certain amount of energy. And based on that, I know how I can control the appliance on accordingly. So if I send the price signal is larger than the price they bid, they will turn off, because they say that it's more expensive. And if I send the price signal lower than it, I can, let them, turn on. Okay, so basically, based on this bit, okay, I can design some, aggregate control action by pricing. So basically, from one household to household, I just aggregate the bit accordingly, and at the end, I have the price responsive curve. Based on that, I know okay how I can adjust the power of the whole HVAC. Okay, one for example here we have 100 HVAC in the distribution grid accordingly. So you can imagine it's like a group controls, of course, but we implement it in kind of linear market design. So we control the power of them, based on the appropriate price signal, and by sending that, okay, we can adjust their energy consumption quite well, follow some targeted load. So there are some implications about it. Of course, this is a normal operation. Okay. The first thing is that flexible load, such as AVAC water heater, can provide something called distributed spatial temporal flexibility to our grid. So it is also a catchy term right now. People talk a lot about it. After the incident in Texas ice storm, we want the energy customer to be more flexible to adapt with the limited resources. So why it feasible to use it to address some kind of Texas ice storm? Currently, I don't have any numerical result and research to highlight that. But the idea behind that is very simple. Okay, so address extreme weather event in the grid, such as preparation and adaptation. Can be done with the active participant of the demand side. This because it's very difficult for the grid utility to prepare to invest for something very extreme with a very low probability. For example, it's very the incident in Texas. Some people argue that it's one of a 30 years event, and it's very difficult. I mean, it's infeasible to predict such ice storm 30 years ahead in order to build a power plant for redundant accordingly, and also it's very costly. However, given a very good weather forecast in short term, okay, we know how we should adapt in short term, given some certain outage will happen in our area. So basically, how to track energy storage accordingly, how to adjust the thermostat, and also by using the smart so smart grid bit-based mechanism. Here we also know how to allocate the limited resources to the customer based on their accessibility of their energy consumption. For example, we can put more priority for customer demand in heating during the ice storm, while we discourage the other energy consumption behavior. For example, playing YouTube or watching a video game, something like that. Okay, so basically, if so, the idea is that with flexibility in short term like this, we can use it to address a long term uncertainty of some extreme weather event. With it, I finish my talk, and I thank you for your time.
Okay, so is it only me that I cannot hear you, or others also lost your audio?
Me?
Okay, yep, I can hear you now.
Okay, so I just finished my presentations.
No, I think before you finish your presentation, I lost your audio for a few seconds, but that was toward the end of your talk. I don't think that we missed so much of your talk. Okay, great. Thank you so much. Thank you for this great talk. Now it's time for questions. Any question to Dr. Nigo? So I'm gonna go ask questions until others are gonna be preparing the questions. I was really impressed by the way that you were trying to kind of distinguish between the definition of reliability and resilience. That was the two terms interchangeably have been used in the literature, but you were trying to make a distinction between these two.
Yeah.
Later, share with me the source,
Yeah.
the literature, sorry, the paper that you were referring to, or the
Yeah.
document you were referring to, as far as the
Yeah.
distinction between reliability and resilience.
Yeah, sure, sure. I will share with you. It's based on the short in I think it's a report of Sandy Anderson lab to be specific, written by Nguyen in 2017. So I can send you this slide and also the documentation. I mean this reference after the meeting. Yeah.
Okay, great. Thank you. Rabbi, you typed your question in the chat box. Go ahead and ask it.
Okay. Yeah, they see the chat box over here.
But you can go ahead and ask it, Rabbi.
Hello, doctor. Good afternoon. Thank you for your
Yeah.
presentation.
Yeah.
My first question about the system protection that you have assumed during your simulation. The objective of the system protection is to isolate the defective region from the rest of the power system. But in your simulation, I find that when the collapse happens, it drastically falls. So I wanted to know what specific type of a system protection you have considered. For example, for the line differential protections, for the transformer, book holes, overload relay, or so on. This is my first
Yeah,
question.
yeah. So yeah, so you're right. So different, we have a different protection scheme. Here we have only focused on the outage of overhead distribution line. Here. And the here we use we assume that we have some kind of distribution automation to isolate the outage line. So basically, we consider about the flow phone isolation and localization system. So so basically we have different sectionalizing switch. So if the outage happen in a part of the line, we assume that the switch will be open accordingly to isolate this damaged line from the grid. And that based on this information, we have the outage scenario and how to and the question is how to optimize the resources accordingly. And for the substation transformer, so basically one an issue about the transformer during the hurricane is the flood, the water will hit the transformer and make it damage. However, modeling a flood during the hurricane is also a very complicated task. So in this one, we assume that the substation is okay during the hurricane. Okay? So in order to model the outage of the transformer also and like substation or the interconnected between the distribution and the transmission, we need to have a good flooding model. But right now in the literature, it's where we cannot see any good model about like modeling the flood during the hurricane in order to integrate it into the power system operation. So this is something the challenge that I'm thinking how to do it in the future. But currently in the literature, there are no flooding scenario model for generating outage scenario. If I know, okay.
Okay, thank you for your response. I do understand that you have made some assumptions there.
Yeah.
Usually for hurricane or such type of weather conditions, differential protections is always activated. That helps to restore the system from the
Yeah.
collapse to a region. I have also another question. So my second question is that usually when we do the simulation of a power system analysis, we consider a slack bus. The objective of the slack bus is to make the system stable. So I wanted to know that what type of conditions you have set during your system restorations for the slack bus. Have you considered any?
Yeah. So one thing is that the slack bus, if the system is okay, the slack bus of the distributed the radio network, right, should be the bus. It's a substation. It's here. Yeah. And I think the question is that in the isolated area, what is the slack bus? So actually, we do not set it, especially in the in the constraint. Basically, if we want to do that, we have to find a birth and put the variable, I mean the voltage equal to 1. But we do not set it. We just set the voltage in a case of 1.1 or 1.2, and also on the constraint must be ensure that after we solve the power flow, all of the voltage should be in the acceptance range. And if it's not, okay, so the solver will find some burst that we have to curtail, because if we do not have power to serve all the load in the isolated area, the voltage will drop, right? So the solver must curtail some load accordingly as a part of the decision variable.
Okay, thank you for your response. In this regard, I have a questions about which type of a specific algorithm you follow. Is it Newton-Raphson's or Gaussian-Seidel approach to stabilize your system?
Okay, so here the thing is the power flow in the distribution network. So solving the power equation, you can use the Newton-Raphson of fast forward backwards. But this one is not it's difficult to include the one in the optimization model. Okay, in optimize. So what here I got a model is a set of mixed integer conic programming. And the thing is that this one is convex. Okay, so I relax an equation as an equality, so it becomes like the convex model, and we can solve it, using the mixed interconnect programming. And the key thing is that in the distribution network with the radial structure, the connect optimization model here is exact to model the distribution power flow. So that means that you solve the power distribution equation by Newton-Raphson, it equivalently to solve a connect optimization problem in the connect form. Okay, so there are some paper for that, and if you look at some code like connect, some keyword like connect optimization for radial power flow, you can see some paper for that. So basically, I try to formulate the problem as a connect programming problem.
Okay, so you have numerically solved the problem. Okay, thank you for your response. And my final question is about the collapse phenomena, because when the collapse will happen or when you would try to restore the system, there is a high chance to collapse. It may be either voltage collapse or frequency collapse, or there might be some other types of collapse. So in your proposed system, which specific type of a collapse you have tried to solve in your resilient system?
Specific collapse from a voltage collapse or frequency. So here's the thing, okay, so there's something related to the transient over here. So I think that it's in the matter of less than 1 minute, we have the phone isolated. We have the automation system to take care about it. How to isolate the phone, how to open the system light switch accordingly. Because basically frequency issue means that when we do not have the power to supply the load, the frequency will reduce over, right? So this is not part of the optimization, okay? So, but in the optimization, what we want to do is that we try to make we want to maximize the amount of customer we can serve, okay? Subject to several operation constraints, including the supply and demand equal, okay, by the power flow. So by doing that, okay, so what we have to do in order to put the number of customer survive during the outage, okay, we have to proactively prepare for that. For example, we have to charge enough electricity to the battery storage, so once the hurricane happens, we still have some energy reserve in order to detect it back to support a customer in the outage area. We also have another thing is that, okay, given the limited energy resources, how we allocate it to a customer in the area. Okay, so we have a lot of demand, but we have a limited supply. Okay, so some people must be stay in the dark for a while. So how we allocate this one? So in reality, it's called rolling blackout, right? So in this paper, what I want to do is that to automate how to allocate this limited power in the fair way. So that's why I use some kind of CIC concept. Okay, how to so as the customer stay in the dark, for a while their priority will increase, and at some point the utility must pay attention to them. So that's it. So for voltage collapse, okay, I have the voltage constraint to make sure that everything within the a certain range, so 0.9 or 1.1. If I cannot do that, okay, the optimization solver will find some bursts that I need to curtail to remain to make sure that the voltage and frequency in the system still stay in the in the a certain range. That's all.
Okay, thank you for your response about the phenomena, especially you are attacking voltage collapse phenomena, and eventually it will also help to improve the frequency. So usually when we are doing the voltage phenomena, it is a technique that bifurcation analysis to bifurcate the point. Anyway, thank you for your presentations, and it was very good.
Thank you. Any other question? Maybe I have one more question. So especially when we come to the resilience concept, and primarily many of these sort of things are either simulation-based or numerical approaches. How about the proof of correctness or guarantee that you can provide? Is it something that you were focusing or not?
So if I understand your question correctly, that most of this is like simulation based, and how we validate, any application concept in reality. So yeah, this is something I would like to do in the future, actually in the near future, because the thing with it is also the issue that faced by a researcher recently, because we propose a lot of optimization and control to improve the resilience of the power grids, but no, it's very skeptical from industry. So we also the thing is that okay, there are two ways to close the gap and to verify the effectiveness of this. One is that to use some kind of very high fidelity um, model to quantify the our solution concept in the system. For example, in this simulation, I forgot because it's optimization model, I shown it in the steady state. Okay, so there are no thing like voltage or frequency dynamic. Okay, in reality, in order to do that, in order to verify something, okay, we have to put this one in some power system simulator where they can simulate different time scale accordingly. So the phenomenon and voltage and frequency or something like volt back control, something can be incorporated. Okay, because one issue, if you realize that if we have a lot of distributed energy resources in the system like that, okay, in steady state it's okay, but in the dynamic state, okay, we have some voltage issue because of the PV. People know that, but it's very hard to quantify it. The other one is that to have some kind of hardware in the loop that can provide the reaction of the power system in real time. So it can provide both dynamic model and also steady state model. So by doing that, any kind of a resilient performance, any resilient enhancement solution, we can verify its actual correctness, its actual performance before potentially implementing in reality. So quantifying the resilient concept using simulation or hardware in the loop is something that people are working right now in the research community, and I also plan to do that in the future.
Great, thank you.
Yeah.
So maybe we have time for maximum one more question. If not, just one announcement for next week's presentation. We will have Dr. Ali Hajbabai as a part of NCCAV seminar series, and he's going to be talking on the connected autonomous vehicles sort of applications. You will going to be receiving the information about the details of the talk and abstract beginning of next week. Okay.
Okay, so thank you, Dr. Homaifan, Dr. Kari Modini, for your invitation. Thank you very much for your time.
Thank you. Thank you so much. And yep, we enjoyed today's talk. And everybody, hope you're going to be having a great weekend. Thank you so much. Bye-bye.